Is that coin you just flipped really heads or tails before catch it and look?
It's a good question. Because what if, like, at the most fundamental level, the act of looking, of interacting, what if that actually defines what's there?
Exactly. Welcome to the deep dive. Because in the quantum world, it seems observation isn't just passive discovery. It sounds more like, well, an active definition.
Mm-hmm. And it's a concept that really fundamentally challenges our intuition about reality. We're diving into what physicists call the measurement problem.
Which is basically the central paradox of quantum mechanics.
Pretty much. Our mission today is to try and unravel
Mm-hmm.
this deep scientific and philosophical challenge and explore how the act of measurement really seems to shape physical reality.
And we've really dug into the sources for this one. We've got a whole stack, articles, research papers, even some of our old notes from grappling with these ideas over the years.
Yeah, there's a lot there.
We want to cut through some of the noise, maybe reveal the how and why behind this pretty astonishing concept. Hopefully, you leave feeling genuinely well-informed.
And maybe looking at the world just a little bit differently.
Yeah, hopefully. Let's get into it.
Okay, so to start, let's contrast the everyday view with the quantum one. Classically, things are, well, straightforward. Objects have definite properties.
Like position, velocity.
Exactly. Whether anyone's looking or not, the observer is just, passive, a recorder. Measurement just reveals what's already there.
Right. My coffee cup is definitely on my desk, even if I leave the room. That feels intuitive.
It does. But quantum mechanics, it makes a radical departure from that comfortable idea. It basically insists the observer isn't passive, they're an active participant.
So the measurement itself isn't discovery, it's definition.
That's the core idea, and this is where we bump into the enigma of wave function collapse. Quantum theory describes an isolated system evolving smoothly, predictably.
According to the Schrödinger equation, yeah.
Right. But the moment a measurement happens, bang, that smooth evolution is like violently interrupted. The system abruptly, probabilistically, collapses into a single definite state.
And that conflict, the smooth evolution versus the abrupt collapse, that's the measurement problem.
That's the heart of it. And what's crucial as you dig into the sources is this idea that maybe it isn't a failure of the theory.
But an insight.
A deep insight into reality, potentially. The sources consistently suggest the method of measurement, the actual physical apparatus you build, is what defines the properties.
So the apparatus selects a basis, a set of possible outcomes.
Exactly. From this sort of indeterminate field of possibilities, the state of a quantum system isn't intrinsic like its color. It seems to be relational, depending entirely on how you measure it.
It's like the question you ask nature dictates the kind of answer you're allowed to get.
Precisely. To really get this, we need to unpack what a quantum system is like before measurement. Superposition.
Okay. So unlike a classical coin hidden under my hand, which is either heads or tails,
Right, you just don't know which.
a quantum particle, say, an electron in a superposition of spin up and spin down, isn't really up or down.
No, it's genuinely indeterminate. It's not about our ignorance. It fundamentally doesn't have a definite spin state along that axis yet.
Wow. Okay. And that's described by the wave function, psi.
Yes, S.
Yeah.
It's this complex mathematical object encoding the whole range of potential behaviors. When a system's in superposition, its wave function is a linear combination of all possible states. It holds all those possibilities simultaneously.
And this wave-like nature is real. It leads to things like interference.
Absolutely. Like
Yeah.
ripples on a pond interfering. The double-slit experiment, which we'll definitely get to, is the classic proof of superposition's physical reality.
It's easy to get tripped up by analogies, though, like Schrödinger's cat being alive and dead.
Right. Those can be misleading.
Huh.
The state isn't a contradictory mix of actual properties. It's more like a coherent state of potentiality.
Yeah.
Multiple outcomes are possible, but they only become definite when you interact, when you measure.
This brings us to a huge debate, right? Is the wave function real or just our knowledge?
The ontic versus epistemic question.
Yeah.
Is I describing objective reality itself oncentic? Or is it just a tool representing our knowledge and predictions, epistemic?
So epistemic means collapse is just us updating our knowledge when we learn the outcome.
Kind of, yeah. That's roughly the Copenhagen interpretation's angle.
But if it's onsent, the wave function is physically real, like a field, and collapse is a real physical change.
Exactly. And interpretations like many worlds or pilot wave theories lean that way. They treat eta as real. And this choice fundamentally changes how you think about measurement. Is it just finding information, or is it physically altering the system?
That distinction between potentiality and actuality seems key. Before measurement, it's actualizable states, potential realities.
That's a good way to put it, potential realities. And measurement is the physical process that converts this field of potentials into one single, definite actual state. The system isn't in a superposition of actuals that's contradictory. It's in a state comprising a superposition of potentials.
Which makes sense why our classical language struggles. We talk about definite things.
Precisely. Think wave-particle duality.
Mm?
An electron acts like a wave here, a particle there. Niels Bohr's idea of complementarity fits here.
Ah, right. Wave and particle aren't simultaneous properties.
So there's mutually exclusive ways it manifests, depending on the experiment. The setup forces one classical description wave or particle, making the other meaningless in that context. Measurement actively imposes a classical framework.
Okay, conceptually that makes sense. But how does this transformation from potential to actual happen formally? What are the rules?
It's not arbitrary. There's a precise mathematical framework. Every measurable quantity and observable, like spin, position, energy, corresponds to a specific mathematical thing called a Hermitian linear operator.
An operator. Like asking the system a mathematical question, what's your spin? Or where are you?
Kind of, yeah. And the answers you can get back aren't just anything.
They're limited.
Strictly limited to the eigenvalues of that specific operator. These are real numbers that correspond to the possible measurement results. Nature's answers are constrained, like multiple choice options.
Okay, so when you measure a system in superposition, what happens then mathematically?
Two key things. First, you get one of those eigenvalues as your outcome with a probability given by the Born rule. We don't need to dive deep into the math, but there's a precise rule for the probability.
Okay, and second,
and this is the collapse part, mathematically, the system's state instantly projects onto the corresponding eigenvector. It snaps into the state associated with the answer you got.
so if it was already in that state, measurement just confirms it. But if not, measurement creates the definiteness.
Exactly. Which means choosing what to measure isn't abstract. Building a calorimeter for energy is physically different from setting up a photographic plate for position. Each apparatus is the physical realization of a specific operator, a specific question.
The apparatus defines the grid of possible answers.
Yes. It physically dictates the framework. As one source put it, the apparatus contrives spectrally to erect its own individual orthogonal scaffold. It sets up the possible outcomes and post-measurement states.
And this next part really makes you think. Rotating a Stern-Gerlach magnet, which measures spin. You're not just changing your viewpoint, you're physically changing the measurement basis. You're defining a whole new, incompatible set of potential realities the electron could collapse into.
That's a fantastic point. The apparatus defines the question and constrains the answers, which leads to the system-apparatus interaction itself.
Right, because measurement is a physical coupling. Microscopic system meets macroscopic device.
But here's the problem. Follow the standard quantum rules, the linear Schrödinger equation, and the apparatus itself should get entangled and end up in a superposition.
Like the pointer needle pointing to -1 and -9 simultaneously. Schrödinger's cat, but for the measuring device.
Exactly, but we never see that. We always observe definite outcomes. A specific number on a screen, a click in one detector.
So how do we get definite results out of what should be this massive entangled superposition?
Well, one perspective is that the mathematics, the fact observables are Hermitian operators, isn't just math. It reflects a physical need to produce stable, distinguishable classical information.
Ah, so a measurement needs to create an unambiguous record.
Right. The possible outcomes have to be clearly different, perfectly distinguishable. So the apparatus is engineered, perhaps through interaction with the wider environment decoherence, to essentially force the system into one of these mutually exclusive states. It makes the information definite.
Even for more complex measurements, like POVMs.
Yeah, those positive operator valued measures, they're sort of more generalized, maybe fuzzy measurements, but they still ultimately boil down to producing well-defined probabilistic outcomes by entangling the system with a larger environment, or ancilla, and then measuring that. The core principle holds. You end up with a definite record.
Okay, this is getting pretty abstract. Let's ground it in some actual experiments, because this is where you really see observation shaping reality. The double-slit is the absolute classic.
It really is. You send individual particles, photons, electrons, whatever, one by one, towards a barrier with two narrow slits. Behind it, there's a detector screen.
And if you don't try to find out which slit the particle went through,
know which way information,
you get an interference pattern on the screen, like waves.
Exactly, which implies each particle, somehow behaving like a wave, went through both slits simultaneously in superposition and interfered with itself. The only measurement is its final position.
But if you put a detector at the slits to see which path it took,
as soon as you get that which way information,
the interference pattern vanishes completely. You just get two clumps behind the slits like you were throwing tiny baseballs through.
Right. The superposition is destroyed by the measurement at the slits. The key takeaway is clear. The conditions of measurement, whether you ask which path, fundamentally determine the nature you observe. Wave or particle, you choose.
Then there's Wheeler's delayed choice experiment. This one is wild.
It really pushes the boundaries of intuition. So a single photon hits a beam splitter. It goes into a superposition of taking two different, often very long paths.
Okay.
The critical part, the decision whether to put a second beam splitter at the end of the paths, which would recombine them and show interference if it took both paths, or not put it there, which would tell you which path it took. That decision is made after the photon has already passed the first splitter.
After it's supposedly already decided whether to take one path or both.
Exactly.
Right.
Sometimes using a random number generator millions of light years away, ensuring no signal could influence the photon's choice.
And the result is mind-bending.
It is. If the second beam splitter is inserted at the last moment, you see interference. It behaved like a wave, took both paths. If it's not inserted, the detectors just click individually. It behaved like a particle, took only one path.
So its behavior back at the first splitter seems determined by a choice made in its future.
It's not really backward causation, but it shows you cannot assign a definite independent history to the photon before the final measurement is complete. The entire experimental context matters. Wheeler's famous quote comes to mind. We have an unavoidable effect on what we have a right to say about the already past history of that photon. The past is, in a sense, defined by the measurement context.
Wow. Okay. And the Stern-Gerlach experiment, another key piece.
Absolutely, especially with sequential measurements. You shoot, say, silver atoms through a special non-uniform magnetic field. Classically, you'd expect a continuous smear on the detector based on random magnet orientations.
But you don't get that.
No, you get distinct packets. For silver atoms, just two spots, spin up and spin down along the field direction. This was the first direct evidence of space quantization. Spin is discrete along any axis you use to measure. The apparatus forces the indeterminate spin into a definite outcome.
And here's where it gets really counterintuitive, right? The sequential part.
Yes. Take only the atoms that went up along the vertical z-axis. So now they have definite z-spin up. Send that beam through a second Stern-Gerlach magnet, but oriented horizontally, to measure x-spin. What happens? You get a 50-50 split, half measure x up, half measure x down. The act of measuring x-spin forces the system, which had definite z-spin, into a superposition of x-spin states and collapses it. Now its z-spin is indeterminate again.
And the real kicker.
Kicker is, if you take, say, the x-up beam from that second measurement and send it through a third magnet, oriented back vertically to measure z-spin again.
You don't just get z up back.
Nope. You again get a 50-50 split. Z up and Z down. The x-spin measurement completely erased the definite z-spin property the atoms had after the first magnet.
So measurement isn't passive reading. It's active erasure and redefinition.
It's an active state-altering process, aggressively resculpting reality, you could say. Each measurement redefines the system's properties relevant to that measurement basis, destroying previous definiteness in incompatible bases.
Okay, so we've established measurement forces a definite outcome. But the standard quantum math, the Schrödinger equation, says the measuring device itself should get caught in the superposition, which we don't see.
Right. That contradiction is the measurement problem. And it's led to this great divide, the different interpretations trying to resolve it.
Tim Maudlin's trilemma is useful here, isn't it, to frame the problem?
Extremely useful. Maudlin points out three plausible statements that can't all be true simultaneously. 1, the wave function is a complete description of reality.
Completeness.
2, the wave function always evolves linearly, according to the Schrödinger equation.
Linear evolution.
And 3, measurements always have single, definite outcomes, which we observe.
Definite outcomes, right? And you can't have all three.
Logically, no. At least one has to go. And each major interpretation makes its choice, denying one of these statements.
Let's start with Copenhagen, the sort of standard textbook view associated with Bohr and Heisenberg.
Right. Copenhagen basically denies statement 2, linear dynamics, It says, sure, A evolves linearly until a measurement occurs. Then something different happens. Collapse.
A non-linear probabilistic jump.
Exactly. When the quantum system interacts with a classical measuring apparatus, its wave function instantaneously and non-deterministically collapses into one specific state.
But the criticism is that it's vague, right? What is a measurement? What counts as classical? Where's the dividing line, the Heisenberg code?
Precisely. It's often seen as more of a pragmatic recipe for calculations, shut up and calculate, rather than a complete description of what's physically happening. Questions about the state before measurement are often dismissed as meaningless.
So it collapses, but Copenhagen doesn't really explain the how or why. What about attempts to make collapse more physical?
Well, there's the von Neumann-Wigner interpretation. It tries to pin down the cause of collapse. Consciousness.
Consciousness causes collapse. Seriously.
That was the proposal. Von Neumann traced the measurement process. Particle interacts with device, interacts with screen, eye, brain. If everything follows quantum linearity, the entire chain, including the observer's brain, should end up in a superposition. Until it hits consciousness. Von Neumann, and especially Eugene Wigner, suggested consciousness is somehow outside the purely physical chain and is what breaks the superposition, forcing a single outcome.
That sounds philosophically tricky. Wigner's friend paradox and all that.
Exactly. If your friend does an experiment in a sealed lab, is the friend plus the lab in a superposition until you open the door and ask whose consciousness counts? It raises huge questions about objectivity, subjectivity, even solipsism.
Okay, moving on. Many worlds interpretation, MWI, Hugh Everett. This one's pretty famous. What does it deny?
MWI denies statement 3, definite outcomes. Or rather, it says there isn't only one outcome.
How does that work?
It claims the wave function never collapses. Statement 2, linear evolution, is always true, universally.
Yeah.
Etienne is complete. Statement 1 holds 2.
So, where do the definite outcomes we see come from?
When a quantum system interacts with its environment or an observer, they become entangled. This process, called decoherence, effectively causes the universal wave function to branch into multiple, essentially non-interacting parallel realities. Each branch represents a consistent world where one of the possible measurement outcomes actually occurred. Collapse is just a subjective illusion experienced by observers within their specific branch. All outcomes happen, just in different worlds.
Wow. Okay. And the last major one, pilot wave theory or Bohmian mechanics?
Bohmian mechanics denies statement 1, the completeness of the wave function. It says A isn't the whole story.
There's something else, hidden variables.
Exactly. It posits that there are actual particles with definite positions at all times. These positions are the hidden variables that A alone doesn't describe.
So it's deterministic.
Yes. The wave function acts as a pilot wave, physically guiding the motion of these actual particles according to a specific guiding equation. The randomness we see in quantum mechanics is just due to our ignorance of the particle's precise initial positions.
How does it explain interference then, like the double slit?
The particle itself goes through only one slit, but its pilot wave goes through both slits, creating an interference pattern in the wave. This wave pattern then guides the particle's trajectory, making it more likely to land in the bright fringes.
And collapse.
Collapse is an effective phenomenon in Bohmian mechanics. After measurement, the different parts of the pilot wave separate in configuration space. The particle is only influenced by the wave packet it's actually in. The other empty wave packets just don't affect its trajectory anymore. So it restores determinism and definite outcomes, but it fully embraces non-locality. A particle's velocity can depend instantaneously on the positions of distant particles.
So, pulling this together, these interpretations aren't just random guesses. They're logical responses to Maudlin's trilemma. You have to give up either completeness or linear evolution or single definite outcomes.
Exactly. You can't have all three if you start from standard quantum mechanics. Each interpretation makes a different sacrifice to restore consistency.
And these choices have really deep implications, don't they? Like for the arrow of time.
Absolutely. The fundamental laws, like the Schrödinger equation, are time reversible. They work the same forwards and backwards. There's no inherent direction of time in the basic dynamics.
But measurement, the collapse, seems irreversible. You lose the information about the other possibilities. It feels like it introduces a direction.
It does seem that way. But the crucial insight, especially from decoherence studies, is that this irreversibility might be emergent and statistical, like the thermodynamic arrow of time from chaos.
Meaning it's not fundamentally irreversible.
Potentially not. Very careful, weak measurements that extract minimal information can, in principle, be reversed, allowing a sort of uncollapse. But a standard, strong measurement entangles the system so thoroughly with the vast environment that reversing it becomes statistically impossible, like unmixing milk from coffee. The forward process is just overwhelmingly more probable. The definite classical record emerges because information gets diluted into the environment.
And then there's non-locality. Entanglement. Einstein's spooky action at a distance.
Right. Linked particles share properties instantly correlated no matter how far apart. Bell's theorem and the experiments confirming it show these correlations are stronger than any theory based on purely local, pre-existing properties, local realism, can explain.
So measuring particle A doesn't just reveal something about A that was already fixed.
No. It seems to actively define the property of its distant partner, particle B, at the moment of measurement. The state of B isn't solely intrinsic to B, it's a non-local, relational property of the whole entangled system, which only becomes actualized in a specific way by the context of measurement performed on A.
That forces a huge reevaluation of what real even means, away from independent objects towards interconnected systems.
Exactly. Reality seems less about isolated bits and more about relationships and context.
So if we try to synthesize all this, the really core revolutionary takeaway seems to be that measurement isn't passive. It's this dynamic, participatory interaction.
Where the observer, crucially through their choice of apparatus, shapes the reality that gets observed.
The apparatus imposes a classical framework, right? It forces the indeterminate quantum state into a definite, actualized outcome.
You ask about waves by setting up an interference experiment, you see waves. You ask about particles by detecting which path, you see particles. You measure spin along z, you get a definite z spin. But X and Y become undefined. The reality we experience is conditioned by the questions we pose through our experiments.
And yet, despite knowing the rules, the math, the effects, the actual mechanism underneath, the thing that singles out this outcome over that one during collapse, that's still the mystery.
That's the deep debate. The how of the quantum to classical transition is precisely where these interpretations fundamentally clash. Copenhagen says it just happens, MWI says all happened, Bohm says it was guided there.
And we can't experimentally tell them apart, at least not yet.
Not definitively, no. Which forces us into these really profound metaphysical territories. What is reality? What is information? What does it mean to exist?
Okay, so let's leave our listeners with a final thought to chew on. If measurement truly defines reality, and our interactions, even just observing, are a form of measurement, what if you, just by existing, perceiving, interacting with the world at our macroscopic scale? What if you're constantly, unavoidably participating in the creation of reality around you? What if the act of living and experiencing is, in some way we barely comprehend, an ongoing act of defining what is real?